All right, we're going to continue on here. Last time we finished up chapter 7, which was sort of the first part of thermodynamics. We're now going to go ahead to chapter 16 for kind of part 2 of thermodynamics and the rest of everything. So in chapter 7, we talked about delta H, which is our change in enthalpy. And it is, again, the heat of a reaction. And again, if delta H is negative, it's exothermic. If delta H is positive, it's endothermic, as we talked about. In this chapter, we're going to talk about entropy, which should not be confused with enthalpy. Entropy is actually delta S, free energy, and sometimes referred to as Gibbs free energy. That's delta G, as we'll talk about. So we use a few different letters. And of course, we can't go too much long in this class without coming back to equilibrium as well. So we'll come back and talk a little bit about K at the end. So in this sort of chapter, definitely in this chapter, we kind of deal with the second and third law of thermodynamics. And the idea of that is we want to know about whether or not a reaction is spontaneous. And sometimes people have sort of the wrong understanding of sort of what spontaneous means. So sometimes people think when the reaction, for example, is spontaneous, it will occur really fast, like snap your fingers and it will occur. And that's not really what spontaneity means here in this chapter. What it does mean is under those particular conditions, will that reaction basically occur without any type of intervention or you doing something to help it along? And that is what a spontaneous reaction basically means. A spontaneous reaction could be really, really fast. It could also be really, really slow. Kinetics deals with how fast or slow a reaction takes place. But when we talk about a reaction being spontaneous, it means basically the way the reaction is written under those conditions. If we just leave it alone, we would expect a reaction to occur. Again, as I said, it could be really fast, could be really slow, but we would expect it to occur without any type of, as I mentioned, intervention to help it out. There's a lot of physical and chemical processes that are spontaneous that we are aware of. Water runs downhill. Water doesn't typically go uphill. If we take some sugar, it will start to dissolve in a cup of coffee. At 1 atmosphere, water freezes at 0 degrees and melts above 0 degrees Celsius. As we talked about in chapter 7, heat flows from the hotter object to the colder, and iron exposed to oxygen with a little bit of water will make rust form. So these are all spontaneous type processes. Obviously, here, if we look at the skiers, the one on the right here going downhill is definitely a spontaneous process, as pretty much the downhill part's going to help them. This person going uphill is non-spontaneous. You're not going to be at the bottom of the hill and magically just get to the top without having to do something, some type of work to get yourself there, like this person went out to do. I'm assuming they do not want to see each other, one coming down, one coming up on the same slope. Probably not a great idea. Now, same idea here. If we have sort of a gas molecules in one side of a tube here, if you open the sort of spout there, it would spontaneously allow those gas molecules basically to flood into the other side. Now, if you started with gas molecules on both sides, they will not just by themselves decide to head over to the right without maybe some convincing or something on doing something to this side to allow them to go to the other side. Now, one of the things we think about is when we think about a reaction and we think about it being exothermic, does that mean that the reaction will be spontaneous? So if we look at the delta H for a reaction and it's negative, can we expect the reaction to be spontaneous? So here's a combustion reaction which has a negative delta H, and that's a spontaneous reaction here, formation of water. This is actually melting of ice, positive delta H, and this is dissolving to make a solution, basically, and that's also positive. So these are all spontaneous reactions that will take place, and as you can see, we got a couple that are exothermic, we have some that are endothermic. So just based on this example here, we can see that just being exothermic does not necessarily mean that your reaction will be spontaneous. A lot of times, being exothermic does favor spontaneity. One of the things that sort of helps with a reaction being spontaneous is the spreading out of energy. And that usually occurs a lot with exothermic reactions as they're giving off the energy and kind of spreading it out. But spontaneity doesn't guarantee a reaction will be spontaneous. Our delta H doesn't guarantee a reaction will be spontaneous. So although it's a good indicator, you definitely can have some spontaneous reactions that are endothermic and some that are exothermic as well. So we can't use delta H as our sort of factor to decide whether or not a reaction is spontaneous. So we do need something else, and that is entropy. And entropy, which is S or delta S, is basically the amount of randomness or disorder there is in a system. As the amount of order increases, the S value or the entropy value decreases. So one of the unusual things for people sometimes is as the order increases, the delta S gets more negative. Yeah, it becomes more negative of a value. As the amount of disorder increases, the delta S actually, the change in entropy actually becomes more positive. So when we talk about entropy, if we have a positive entropy value, what that means is overall from where you started to where you end, there is a lot more disorder happening. And one of the easiest places to sort of see that is in a phase sort of change. Obviously, things in the solids phase are ordered pretty well with each other. They're tight. They don't have a lot of energy. That has less entropy than, say, in the liquid phase, where they're still pretty tight to one another, but they have a lot more energy. So there's a lot more movement happening and a lot bit more disorder. Too, obviously, there's a lot of randomness and disorder happening in the gas phase because everything is flying around, right? So I think about it sometimes like how many things are flying in your face as the amount of disorder happens. So things in the gas state have a much higher entropy than things in the solid state typically, again, because they are flying around. So when we look at something like this, which is our ice going to our liquid water, we're going from a state of more order in the solid state to a state of less order and more disorder. And we would expect the delta S in this case to be a positive value. Any questions on that there? Now, when we talk about disorder, it is related to probability. And a probable event is one where there are many ways that it could happen. An improbable event is one where there is only a few ways to sort of accomplish it. So, for example, if we were in this room and we need to escape, it is pretty probable we could get out because there's multiple doors that we can get out from. If we were in this room and we needed to escape and there was no doors, just one small window up there on the top of the ceiling, that's probably more of an improbable event for everybody to get out because there's only one way to basically escape this particular room. So an ordered event or an ordered state has a low probability of occurring and it has a small entropy. A disordered state has a very high probability of occurring and a large entropy. You're more apt to screw something up than you are to do it right, right? So there's only a few ways to do something right, and there's a lot of ways that you could kind of screw something up, right? So there's a greater chance of screwing something up than maybe doing it correct. And one way that we could relate entropy to probability is what is sometimes referred to as the Boltzmann equation, and that is this one here. That is the entropy That is the Boltzmann constant, which is on the bottom here. And natural log of W, and W is the number of microstates there are. Microstates are, if you want to think about it, kind of different ways you can accomplish something, if you will. So if you were at like the carnival and you came up to the game where they're like, hey, if you want to win the big stuffed animal, you need to get all 4 balls on the left-hand side, right? There's really only one way that you could achieve that. There's really two, but it's kind of the same thing, left or right, basically. Now, if you're like, well, maybe get a smaller stuffed animal, if you get 3 on one side and 1 on the other, there's 4 different ways you could accomplish that. And you get the constellation stuffed animal down here if you can at least get 2 on each side. And there are 6 different ways that you can sort of accomplish that. And the one with the lowest entropy in this case would be the one with the smallest number of microstates. And that is, if you just think about it mathematically here, when I put in 1 for my W, natural log of 1 is 0, which means in this case, my entropy would be 0, or a very small sort of value. And that would be different than if we did the natural log, for example, of 6 down here. S would equal K natural log of 6. That's about 1.79, I think, times K. So you're going to get a much larger entropy value here with more ways of achieving that. So Boltzmann equation uses microstates, and again, the more ways you could do something, the higher the probability of that occurring, and the higher the entropy value will be. Any questions on that there? These are all processes that lead to an increase in the entropy of the system here. Here we have something in the solid state, as I mentioned before. When it goes to the liquid state, definitely a lot more movement, a lot more craziness happening. As we go from the liquid state to the gas state, again, our molecules are now flying around and a lot of disorder. When we actually make a solution by dissolving a solute and a solvent together, that actually creates a lot of disorder. Again, before you dissolve your solute, it's probably fairly well organized in a 3-dimensional pattern. Also, for example, your water is also pretty well arranged. They're all the waters hydrogen bonding to each other in a nice organized sort of fashion. Obviously, as you dissolve it, you're breaking apart water-water interactions, you're breaking apart solute-solute interactions, and now you got all these ions that are floating around in the solution. And again, that's going to cause a greater entropy. Temperature, again, a very common way that you can increase the entropy of a system. By increasing the temperature, everybody gains more energy. As they gain more energy, they fly around more, a lot more disorder. And again, that would increase the entropy of the system. All right, so take a few moments here, and for each of these, decide, does the entropy of the system increase or decrease in each of these situations? Okay, let's take a look. So first one here, we are condensing water vapor. So condensation means going from gas to liquid, and obviously we're going from a state of more disorder where everybody's flying around to a state of more order here, and that means that our entropy would be decreasing, and we would expect delta S here to actually be a negative number as a result of that. Any questions on that one there? Forming sucrose crystals from a supersaturated solution. So a crystal here is a very ordered sort of arrangement. You're essentially going from liquid to solid, and that again is creating a lot more order, a lot less disorder, and that will then mean that we would see the entropy start to decrease, and again, the delta S here would be more negative. As we go from 60 to 80 degrees, heating hydrogen gas, an increase in our temperature is going to make those gas molecules move around a lot faster, causing a lot more disorder as they're flying around. And we would see an increase in the entropy. That means when we increase the entropy, we would expect a more positive value for our delta S. Lastly, sublimation of dry ice, and sublimation means we go from solid directly to gas, skipping the whole liquid and clean up there. And in that case, definitely in the gas phase, they are moving around a lot faster. So that's increasing the entropy. Delta S here should be a more positive value in this case. Any questions on any of those there? All right, so entropy, as we talked about in chapter 7, is a state function. And again, a reminder that state functions, as we talked about, are not really determined by sort of how you got there. They're really determined by, again, the two important sort of information, which is sort of where you started and where you ended. As we talked about back then, and again, just a reminder that when we look at a chemical reaction, again, our reactants to our products, this is sort of like our final state in the reaction. This is our initial state in the reaction. And again, that is why we oftentimes with these thermodynamic sort of properties do like products minus reactants to calculate their sort of value. When you look up in a table some entropy values like this one here, and you have a similar table in your book, and usually in the back of the book, there's a big old table of all the thermodynamic sort of values together, H's, S's, and G's in the table. A couple of things that are a little bit different in terms of what you will find in those tables for delta S as compared, say, to delta H. And in this situation, delta H, as we saw, is typically in units of kilojoules. Delta S is typically given in units of joules. And we will see an equation or a formula where we do use both of these guys together. So you do have to watch out for units a lot in this chapter. You oftentimes have to convert it a lot of times kilojoules to joules or joules to kilojoules. Otherwise, you will find yourself off by a factor of 1,000. Another different thing that we see with S is, if you remember when you looked up in the delta H formation table, the delta H for things in their standard state, their values were 0. So if you had just like copper metal or hydrogen gas or nitrogen gas or oxygen gas, those things had a value of 0. For entropy, thank you, you will actually find values for things like that. So as you can see here, something like O2, you will actually find a value for it in the table. Also, different is the entropy values you find in the table. They are all positive values. So they're all positive values as opposed to delta H's that we saw. Some are negative, some are positive as well. So the first law of thermodynamics is essentially what we talked about in chapter 7, and that's the idea that energy can be converted from one form to the next, but we do not create nor destroy any energy. That's, again, our conservation of energy. The second law of thermodynamics is what we're talking about here in this chapter, which is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So in order to use entropy to determine whether or not a reaction is spontaneous, you actually have to calculate what is sometimes referred to as the delta S of the universe. And the delta S of the universe basically is composed of two things: the delta S of the system, or the reaction, and the delta S of the surroundings. So if you calculate the delta S of the universe and you do get a positive value for it, it will mean this reaction will be spontaneous. Obviously, if you calculate the delta S of the universe and you get a negative value, it will tell you the reaction is non-spontaneous. If you calculate the delta S of the universe and you get a 0 for the value, that means that the process is at equilibrium. There is kind of no net change because when something's at equilibrium, it's going forward and backwards at the same rate, which means not much is changing in terms of disorder at that point. Everybody's kind of locked into their concentrations. So we're going to talk about how to calculate each of those things, the delta S of the system and the delta S of the surroundings. We will start with the delta S of the system. And again, sometimes people refer to that as the reaction, as the reaction is typically the system that we're interested in. And to calculate that, you essentially do what we did for delta H. Delta S of the reaction is basically our delta S of our products minus the delta S of our reactants. So just like we did in chapter 7 with delta H, we would go to a table, we would add up all the delta S values for the products, and then subtract it from all the delta S values from the reactants. We also still need to, like we did with delta H, take the coefficients into account. So in this case, the delta S of the reaction would be 4 times the delta S of D minus 2 times the delta S of A plus 3 times the delta S of C in this case. So you do have to take those coefficients into account, and that will allow you to calculate the delta S of the system or the reaction. So why don't you give it a try? I think, okay, let's take a look. So again, this situation, kind of like delta H, if you're just given a reaction, pretty much you should go to that table and find all the values here. So we're going to calculate it, basically our products minus our reactants. So our delta S here of our reaction going to be on our product side. We have 2 CO2, so we're going to take 2 times my value there for CO2, joules per Kelvin per mole. That's essentially all my products. Then I'm going to subtract it from my reactants. I got 2 COs, which is 2 times 197.9. Plus, I do have 1 O2, so it's basically 1 times 205. And that'll take care of all my reactants. So we end up with looks like negative 172.8 joules. Now, it is important to remember that this value here that we just calculated is the delta S of the system. It does not tell us if this reaction is spontaneous or non-spontaneous. It just tells us, in this case, the reaction is actually increasing the order, right? We're decreasing the disorder. We're increasing the order. We got a delta S of a negative. By the way, one of the nice things about this chapter is you could oftentimes make the prediction as to what type of sign you should see on your delta S. So for example, if I look over here on my reactant side, I have a grand total of 3 gas molecules that I'm starting with. If I look on my product side, I have 2 gas molecules. So I went from a situation where I had 3 gas molecules flying around to a situation where I only had 2 gas molecules flying around. So I went from more disorder to more order in this situation because I decreased the number of gas molecules, and that would allow you to predict that the sign here should be negative, which is what we got here. So again, that should oftentimes kind of match up. If you ended up with a positive value here, then something probably went wrong there in the calculation. Any questions on that there? So as I mentioned before, you can oftentimes make a fairly good prediction, and that happens in a lot of questions in this chapter. They oftentimes will not give you numbers and stuff like that. They'll just kind of give you situations, and they'll ask you, based on the sort of the situation, do you expect this to be maybe spontaneous or non-spontaneous or what's happening? So one way that you can look in terms of order increasing or decreasing is by looking at the gas molecules like we just did in that last example. If you actually end up with more gas molecules than you started with, then the opposite would have happened. We would expect our delta S for that reaction to be more positive because we're going from less gas molecules to more gas molecules, and that could cause a lot more disorder and a more positive value for delta S. As we saw in the reaction there that we just did, when it decreases, we would expect the delta S to be negative as we are creating a little bit more order. If there is no net difference in gas molecules on the left-hand side or the right-hand side, then it's sort of a toss-up. It could be positive, it could be negative, but it'd probably be a relatively small value for delta S because it's fairly close. So without doing a calculation, obviously here for the bottom, would you predict the sign of delta S? Should it be positive or negative? So take a moment and think about it. Here on the right-hand side, we only have one gas molecule, as that's a solid. Over here, that is a solid, so that is 0 gas molecules. So again, we're going from a situation where one thing's flying around to no things flying around, so a little bit more order happening here. We would expect the delta S here to be a negative value in this particular case. Any questions on that there? All right, so now that we talked about how to calculate delta S of the system, let's talk a little bit about the delta S of the surroundings and what's going on in that situation. Now, in an exothermic process, as we know, heat and energy is released, and our delta H value, right, would be a negative number. And in an endothermic process, delta H would be a positive number as energy is being absorbed by the system. Now, when we're talking about the entropy of the surroundings, in an exothermic process, the heat and energy that's coming off from the system to the surroundings will cause an increase in temperature of the surroundings and thus allow everybody to gain a little bit more energy and cause a little bit more disorder to occur in the surroundings in this case. And we would expect the delta S of the surroundings in this case to be a positive value, as it will increase the disorder in the surroundings as it picks up that energy that's coming from the system. That is opposite of what will happen in the endothermic case. The heat and energy is coming into the system. The result of that is the surroundings is going to lose energy, and that's going to make everybody in the surroundings start to move a little bit slower. And that's going to allow them to be a little bit more ordered in that case. And we would expect the delta S of the surroundings to be a negative number in this case, as it's losing that energy and becoming a little bit more order. So the entropy is related to the delta S of the surroundings. The delta S of the surroundings is proportional to negative delta H of the system. So what does that mean? It means basically this: delta H of the system and delta S of the surroundings. So if you have a exothermic process, the delta H is going to be negative, and the delta S of the system basically is proportional to negative the delta H. So a negative and a negative will turn the surroundings into a positive value. If you have an endothermic process, your delta S and H of the system will be a positive number. So negative of the delta H will give you a negative times a positive, which will still be a negative number in this case. So that is the relationship. It's basically opposite relationship of the delta H value. Now, does the surrounding temperature play a role in this? The answer is yes. So for example, if you had an exothermic reaction and the surrounding temperature was really, really high, the amount of energy coming off of that exothermic reaction will probably not make a big difference in terms of the disorder in the surroundings, because it was already at a pretty high temperature. So a really bad sort of example of that is if you lit a match, sort of like in this room, a regular room, you could feel the heat coming off the match, right? Because the surrounding temperature is not all that warm. But if you lit a match and you put it in a oven that's already at like 500 degrees, probably the heat coming off of the little match in that sort of temperature of the oven is not going to make a great difference in terms of the added energy happening because it's already really, really hot. Obviously, you don't do any of those things. But if we are starting at a really high temperature in the surroundings, we will see a maybe minimal sort of change in the entropy of those surroundings because it's really high. Also, as well, if we start at a really low temperature in the surroundings, we will see probably a greater sort of entropy change, right? Because that added energy is going to be a little bit more well received. So when we talk about the delta S of the surroundings, that is the formula that we could use. Is a little messed up, so I'll just rewrite it here. Delta S of the surroundings is equal to negative delta H of the system or the reaction divided by the temperature in Kelvin. Yeah, so it has to be in Kelvin. And that will allow you to calculate the delta S of the surroundings. You could calculate that along with the delta S of the system by doing product minus reactants. And again, now you can calculate everything you need to calculate the delta S of the universe and determine whether or not this reaction is going to be spontaneous or not. Any questions on that there? All right, so why don't you try one here then? Here's some values. What is the delta S of the system, the surroundings, and is this reaction spontaneous at 25 degrees Celsius? Okay, let's take a look. So really, again, as we talked about, you gotta calculate delta S of the universe to determine if it is spontaneous or not. That's the delta S of our system plus the delta S of our surroundings. So we'll start with our system here, our reaction. And again, that's going to be our products minus our reactants. So starting with our products here, we have 2 times the value. If it wasn't given to you, you'd find in a table, 193 joules per Kelvin per mole. That's going to take care of our products. That's going to be minus our reactants. 1 times our N2 value there, 192. We're going to plus it to our other reactant. 3 times our H2, 131 in this case. And that's going to get us here a 2 times 193 minus 192 plus 3 times 131, a negative 199 joules. Again, a reminder that that number alone does not tell us whether or not this reaction is spontaneous. It does tell us that we are decreasing the disorder or increasing the order, whichever way you want to look at it. And we can see that and predict that from just the equation. That's 4 gas molecules to 2. So we're creating a lot more order, and we would expect our delta S of our system to be a negative number. First off, any questions on that so far? Now that we have the system, we could do the surroundings, which is negative delta H over T. And in this case here, we are given the delta H, and that's going to give me here negative 92.6. I'm going to times it by 1,000. The reason I'm doing that is to convert it to joules. And I'm doing that because my system are in joules. That way everybody will be in the same units. Again, you got to be careful with the units here. We do want to convert our temperature into Kelvin. So that's a 298, obviously by adding 273 to 25. That's going to give us a 92.6 times 1,000 divided by 298. Going to give us about 311 joules for our surroundings. That also makes sense. We're at 25 degrees Celsius, which is kind of a normal temperature. This is an exothermic reaction, which means the system's giving off energy to the surroundings, and we would expect the surroundings to pick up that energy and cause a lot more disorder and a positive value for the surroundings entropy. Now that we have both of them, we could calculate our universe by adding them, and this is really where units come into play. I can't tell you how many people will add these together with one being in kilojoules and one being in joules and get the wrong answer. So it doesn't really matter necessarily which one you convert it to, but you do have to do that conversion. Otherwise, you will be off, obviously, on your answer. And that's going to give us 112 joules in this case. And that delta S of the universe is a positive value. And because that is positive, that would mean that this reaction is spontaneous because of it. Any questions on any of that there? This is also a really good example of a reaction that's spontaneous, but very slow if you don't use a catalyst. So even though this reaction will occur, it will occur really, really slow if you don't use a catalyst to speed it up, but it will still occur. Any questions on where any of the numbers came from or where we got any of them? All right. So let's talk a little bit about the third law of thermodynamics, which is the entropy of a perfect crystal substance is zero at absolute temperature. And as we go from, obviously, as we see here, our solid to liquid to gas, we are increasing the entropy and obviously decreasing as we kind of go in this direction. The only way to make a perfect crystal is be perfect. There's only one way to do that, which means our delta S based off the Boltzmann equation would equal zero. Remember, as we do phase changes, as we'll talk a little bit about in this chapter, we do see the entropy change as well with it. There is, much like what we talked about as we go from solid to liquid and liquid back to solid, the delta H of fusion, which is the energy needed to do nothing more than change the substance from solid to liquid or liquid to solid without changing the temperature. And that occurs at the normal melting point and freezing point. For something like water, for example, it's like 6.02 kilojoules per mole is the delta H of fusion. That would be right about there. There's also right here, which is the transition from liquid to gas, or gas back to liquid. That is the delta H of vaporization. And that is the energy, again, required to change a substance at its normal boiling point from liquid to gas or gas back to liquid, not changing the temperature. And that is why that's sort of flat in terms of the temperature here. That is what's happening here. That's also what's happening at this point as well. For water, it's roughly 40.6 kilojoules per mole, or around 2,260 joules per gram, are approximately 335 joules per gram here. So you can see, just looking at these numbers as well, it is a lot more energy required to do that transition as you go from liquid to gas than it is as you go from solid to liquid. And that's because as you go from solid to liquid, everybody's still relatively close to one another. But there is some more movement as you go from liquid to gas. Everybody has broken apart from one another. So it takes a lot more energy to kind of do that transition. There is also an entropy change, as we'll talk about later on in this chapter, that involves those transitions. Any questions on that there? So the next thermodynamic sort of property we're going to talk about is Gibbs free energy. And that is another new letter here, delta G. Delta G is Gibbs free energy. It is pretty much what the name sounds like. It is energy available to do some type of work. So that is what Gibbs free energy is. I can do some type of work on something, or work can be done on somebody else. So as we saw with our delta S, you have to calculate delta S of the universe to make that determination as to whether or not a reaction is going to be spontaneous or not. With delta G, you actually don't. You could actually just calculate the delta G, and it will tell you whether or not the reaction is spontaneous or not. There is about 4 different ways that you could calculate delta G, and we'll see kind of those 4 different ways as we go through the rest of this chapter. But my advice is always choose the way that kind of fits the information that's given to you. So this is one way that you could calculate it here. The delta G is equal to the delta H minus T delta S. Now, this is an equation that you would use, for example, if you have the delta H or the delta S, and you can plug it into here. This is also an equation where, as I mentioned before, you do have to be careful of units. That is in kilojoules. That is in joules. So if you do not do the conversion, you will be off by a factor of 1,000. So it's really important to convert it. It's really up to you whichever way you want to convert it to. I will say that delta G is typically given in kilojoules, just like delta H is typically in kilojoules. Delta S, as we saw, is typically in joules. So those are the typical units associated with these guys here. Temperature here obviously still needs to be in Kelvin, like kind of normal, if you will. Now, if you calculate the delta G and it is a negative number, the reaction is spontaneous in the direction that the reaction is written. So it would be spontaneous going from reactants to products. If you calculate delta G and it's a positive value, that means the reaction is non-spontaneous the way it's written. It's basically not going to go to the product side. It's going to kind of hang out on the reactant side. The reaction would be spontaneous if you reversed it. So if you flip the reaction around, the reaction would then become spontaneous. And that is because your products would become your reactants and your reactants will become your products. If you hit the delta G and it's at 0 or equal to 0, the reaction is at equilibrium, basically. Now, that's one way you could calculate the delta G. Here is probably another very common way you could calculate the delta G. And it's the same way we calculated delta H and also delta S. Delta G will equal our delta G of our products minus the delta G of our reactants. So once again, you would go to the table and look up the values for delta G, making sure you hit everybody that is in the correct state. Much like delta H, delta G will not have values for things like H2, O2, copper. They will have values, but those values are 0. So really only S's will have values for those things. And you could add up your products minus your reactants. When you go to that table, that is sometimes referred to as the delta G of formation, or the Gibbs free energy of formation, or standard free energy of formation. And you may be wondering, again, what the little knot sort of means. And typically when you see the little knot here, around figures, that usually means that those things are done under standard conditions. And when we talk about standard conditions, what does that really mean? It really means that if you're dealing with any type of pressure, all the pressures are 1 atmosphere. If you're dealing with any type of concentrations, the concentrations are 1 molar. Not truly standard conditions, but most table type conditions are either 1 atmosphere, 1 molar, and 25 degrees Celsius. So even though the temperature oftentimes is included, it's really not part of standard conditions, but it is sort of the temperature that most things are done in tables. So if you ever look at a table and kind of see the conditions, those are usually the 3 conditions you see. It was 1 atmosphere, 1 molar, and 25 degrees Celsius is typically the thing. But technically speaking, standard conditions, 1 pressure, 1 atmosphere, and 1 molar conditions. So usually if you go to the table and look up those values, you're usually calculating the delta G, for example, or the delta H or the delta S under standard conditions. And you oftentimes see that little kind of circle or knot used as a result of that. Any questions on that there? All right, let's try one here. What is the standard free energy change for this reaction? You got some values on the bottom there, I think. O2 would be 0 kilojoules per mole. Okay, let's take a look. So again, you would obviously go to the table, look these values up, and obviously that would be the approach here. If you have this in a problem, that's the only thing given to you is just the equation. Go look up the delta G values. So we'll do our delta G of our reaction here, going to be our product. So 12 times our CO2, which looks like negative 394.4 plus 15, no, plus 6 times water's value there, negative 237.2. That's going to take care of all of our products minus our reactants. 2 times our C6H6, 124.5. Plus 15 times 0, basically. And that's going to get us here 12 times minus 394.4 plus 6 times negative 237.2 minus 2 times 124.5, about negative 6405 kilojoules. First off, any questions on the calculation there? That is a negative value here. So delta G is negative, which means this reaction should be spontaneous the way it is written. Any questions?